This is a video on abstract inequalities, and we'll be proving that the inequalities given in the question are true. For all of these questions, an important piece of information to remember is that anything squared is always greater than or equals to 0. And we're dealing with real numbers the whole time here, so that's definitely going to be true for every instance of these examples. In these questions, we try to keep our eyes peeled for any instances of perfect squares. And if we see a perfect square, we try to write it in square form. So here in this example, we're asked to prove that x squared plus 2xy plus y squared is greater than or equal to 0. So you might recognize here the pattern of a square. So I can actually take this and write the left-hand side of the inequality as x plus y squared. Note that if I was to put that in on the left-hand side instead of the x squared plus 2xy plus y squared, x plus y squared is definitely greater than or equal to 0 because it's something being squared. So I can write that statement down. It's a good idea to just give a brief reason if you're making a statement. And my reasoning is just that a square is always greater than or equal to 0. But of course, these two expressions are equal. So instead of writing x plus y squared, I can say x squared plus 2xy plus y squared is greater than or equal to 0. I'm going to use the this implies symbol because I'm getting this line from the previous line. It follows on from it. You can stick a little QED at the end if you like to kind of finalize it. So in example 2, we want to prove that x squared plus 2ax plus a squared plus b squared is greater than or equal to 0. So at the beginning of this, like I said before, you're looking for your perfect squares. Just watch out. It might be quite tempting to say that a squared plus b squared is a perfect square, but actually I'm more inclined to look at these first three terms all together, x squared plus 2ax plus a squared, because this is definitely the expansion of a square. And I have this extra little bit, this plus b squared at the end, but that's actually fine because that b squared is itself a square. So I'll be able to split my statement up and make a decision about the features of this first portion and the second portion, and then reassemble it to kind of get to the end of my question. So x squared plus 2ax plus a squared is x plus a squared. So I'm just making that statement first of all. And then of course, because that's a square, I know that it's greater than or equal to 0. And of course, I'll give my reasoning for that again. But that isn't the entire statement on the left-hand side because I haven't included this b squared. So I'll make a statement about the b squared separately. And again, I'll give my reasoning. And again, it's because a square is greater than or equal to 0. And then what I want to do is I want to put these two things together because that creates my original statement. So let's just have a think for a second. So if this is greater than or equal to 0 and this is greater than or equal to 0, then when I put them together, well, they must make a total of 0 if they're both 0, or something greater than 0 if they're greater than 0. So I can just state that x plus a squared plus b squared is greater than or equal to 0. And then this brings me back to the very first line, which is the x squared plus 2ax plus a squared plus b squared is greater than or equal to 0. And notice that once I had determined that each part of it was greater than or equal to 0, I didn't just dive back into that last statement. I kind of cautiously put them together and said that together they were greater than or equal to 0, and then went back to that initial statement to kind of finish off my abstract inequality proof. And again, I can stick a QED there at the end. That just means I'm done. Okay, so here's example 3. Right, so I've got x squared plus y squared is greater than or equal to 2xy. And we've said all along that the best way to go about these questions is to look for perfect squares and then know that they're positive. Well, okay, I've got a square, which is my x square, and I've got a square, which is my y square, but individually they're positive. But do I know that they're bigger than 2xy? It depends what the x and the y are, I suppose, really, doesn't it? So, right, I can't really do it that way. That's quite tricky. Instead, what I'm going to do is I'm going to rewrite this statement completely by bringing this 2xy over to the left. And instead of having it as a statement greater than or equal to 2xy, I'm going to make it be greater than or equal to 0. Now notice I'm not stating for a fact that x squared plus y squared minus 2xy is greater than or equal to 0 because I just don't know yet. I'm asking the question, is it? So let's have a look at this. X squared plus y squared minus 2xy. I might be more inclined to write that in this order instead, x squared minus 2xy plus y squared. And you might recognize now that this is actually a perfect square. So what would this be if it was written in square form, do you think? So this is actually x minus y squared. Okay, so now I know that x minus y squared is definitely bigger than or equal to 0, and I can give my reason for that. And of course, if that's true, well, it implies that x squared minus 2xy plus y squared is greater than or equal to 0, because these two things are equivalent, like I've just stated back up in this line previously. And then I can just rearrange this to make it look like the line that I was trying to prove. And QED at the end. So quite often you're going to encounter questions of this type where you do have to do a little bit of rejigging. I mean, in this question, it's not very much. It's just bringing the 2xy across. But sometimes you might have to do a bit of multiplication first, or maybe tidy up a little bit in the original question so that you can rearrange it into a format where you can find a perfect square. Okay, so let's have a look at a slightly longer example. And in this question, we're asked to prove that p plus q squared is less than or equal to 2 times p squared plus q squared. Okay, so this is an example of where I need to do a bit of tidying up before I can begin to prove anything. So first of all, I've got p plus q squared, so I'm going to expand that. And the reason that I'm going to expand it is because although I'm normally looking for perfect squares, you can see here that the right-hand side of my inequality isn't a 0. And I've got a bit of multiplication over here too, so I probably need to just multiply all of this stuff out and then see if I can rearrange it into something that works for me. So I'll do the p plus q squared first. So that gives p squared plus 2pq plus q squared. And then I'll multiply out the right-hand side as well. Okay, so I've multiplied out both sides of the inequality. Now, I still don't know if the inequality is true, so I'm not going to write it down as a statement. I'm going to write it down as a question. So this is what I'm asking. Is p squared plus 2pq plus q squared less than or equal to 2p squared plus 2q squared? Right, okay, I'll bring everything over to the left-hand side. And you'll notice that I'm not completing my inequality here. I'm just taking everything over to the left, and I'm going to tidy it up a little bit. So if I was to bring everything over to the left-hand side, what I would end up with is minus p squared plus 2pq minus q squared. So if I brought that over to the left, I'd have a 0 left on the right-hand side. So I'd end up with this. No definitive statements so far, aside from just my multiplications. I don't know if it's less than or equal to 0. I'm not going to make a statement that it is. I'm asking a question, is it? Okay, this looks quite similar to the perfect squares that we've seen in our previous examples, but it's a bit funny because I've got a minus here and I've got a minus here. And also, if you look back on those three examples, you'll see that in each case, I was looking at a greater than or equals to 0 on the end of the inequality, whereas this time it's less than or equal to 0. Right, so if something squared is definitely greater than or equal to 0, what do you think I'd need to be able to state that something was definitely less than or equal to 0? Well, if I multiplied that square by minus 1, or if I had minus x squared, that would definitely be less than or equal to 0. So we're going to see, can we construct a negative perfect square on the left-hand side? Okay, simpler than it sounds. The first thing that I'm going to do on the left-hand side is I'm going to factorize out a minus. So if I do that, I end up with minus and then p squared minus 2pq plus q squared. Well, what I have here inside in the bracket looks a bit familiar to me. It looks like what I've been getting at towards the end of my previous examples. It looks like a perfect square. So how else could I write it? So this part in the bracket here, the p squared minus 2pq plus q squared, is actually p minus q squared. So if I'm minusing all of this, then what I have is minus p minus q squared. Now I can make a statement about this and whether it's greater than or less than 0. It's a square, and normally squares are greater than or equal to 0, but it's a minus square. So I can confidently state that a minus square is less than or equal to 0. And again, I'm making a definitive statement here, so I need to back it up with a reason. So a minus square is less than or equal to 0. And now I'm going to link it back through the stages that I brought it through. So this minus p minus q squared came from this line here that I was asking about, minus p squared plus 2pq minus q squared. So if this is true, then this line must be true. So I've linked back to that. And the previous question that I was trying to figure out was, is p squared plus 2pq plus q squared less than or equal to 2p squared plus 2q squared? So I'm going to link back to that next and state that it implies that that's true. So I've stated that that's the case. And then that originally came from the original statement of the inequality that I was trying to prove. So I can link now back to that. And once I've arrived back at the final statement, I'm then finished. QED.